Good evening. Sorry I wasn't able to properly end my previous discussion. So let's continue. We are now on don't care conditions. This is a topic in section 1.3, which is about gate level minimizations. So don't care conditions. Functions that have unspecified output for some input combinations are called incompletely specified functions. In most applications, we simply don't care what value is assumed by the function for the unspecified minterms. For this reason, it is customary to call the unspecified minterms of a function don't care conditions. These don't care conditions can be used on a map to provide further simplification of the Boolean expression. So let's see an example of what are these don't care conditions. Simplify the Boolean function f of w, x, y, z, which is equal to the summation of the minterms 1, 3, 7, 11, 15, which has the don't care conditions d of w, x, y, z, which is equal to the summation of 0 to 5. So it specified the function. It says that it is the summation of the minterms 1, 3, 7, 11, 15, and then it also specified the don't care conditions, meaning the value, the don't care conditions, which is the summation of the minterms 0 to 5. We don't care the value of the minterms 0 to 5, so whether it's 1 or 0, we just don't care. So how can we use don't care to simplify further our function? Excuse. The symbol that we are going to use for don't care conditions is the symbol x. So this is a for variable function. We need to use the for variable k-map. 0, minterm 0, we know that it's in this position. 0 to 5, so 0, 1, 2, so this is, we put x in minterm 2, in minterm 0, and in minterm 5. So 0, 1, 2, 3, 4, 5. That's why we have another x here. And let's not forget the minterms for the function. We have 1, 3, 7, 11, 15. Excuse. So 0, 1, we write 1 in minterm 1. 2, 3, minterm 3, 7. Where is 7? We count 0, 1, 2, 3, 4, 5, 6, 7. Minterm 7 is here. 11. So 8, 9, 10, 11. We put 1 here in 11, minterm 11. And then 15. 11, 12, 13, 14, 15. So another here. Right. So there we have our k-map with the don't care conditions and the minterms. Excuse. Since we don't care what the value of the don't cares are, of the minterms with the don't care conditions, we can assume that they take the value 1, so we can include them in the simplification. So we just need to cover all the ones. So we can cover this here and another row here. If we disregard the don't cares, then we will just have these two squares, adjacent squares. But since we have the don't care, we can simplify further and include the entire row here, which means that we will have lesser variables in this term. So what is this? The equivalent function, simplified function. This column here, that's yz is equal to 1, 1. this column is yz is equal to 1 1, or yz. The term is yz. So we have solved in this part here. How about here? This is wx is equal to 0 0, or in terms of the variables, it's w prime x prime since both are 0, this row here. So it's w prime x prime since wx is equal to 0 0. Therefore, the simplified function is equal to yz plus wx w prime x prime. That's another way of looking at the K-map. That's another way of simplifying with the don't care conditions. Shown here in letter B is another example, another process or way that we can simplify the function. So for this column, it's the same as with the letter A. It's yz. But for the upper ones here, we can use this square, this 4 adjacent squares, and instead of the entire row with the don't cares, we use this don't care and M5 excuse me, to have our square. And what is this function term? What is this function term? This is z is equal to 1. About z is common, which is 1. 0 1 1 1, common is 1, and that is the variable z is equal to 1, or z. But we need to include, what is this row? So we have the variable. So what is this? 2 rows here. If this is w is equal to 1, w is common, which is equal to 1 here at the lower. And these 2 upper rows, w is common and w is equal to 0. So it means w prime will be used. So w prime and then z. That's why we have this term w prime z. So f is equal to yz for this column, and for this 4 squares, w prime z. So we can use either this f is equal to yz plus w prime x prime, or f is equal to yz plus w prime z. Thus, f is equal to yz plus w prime x prime, or f is equal to yz plus w prime z, which are simplified with the use of don't care conditions. Okay, let's go to some circuits. We have the NAND circuits. We know that NAND is the complement of the AND gate. The NAND gate is said to be a universal gate because any logic circuit can be implemented with it. So NAND gate is called a universal gate. Let's show the evidences. For example, we have the inverter, the AND, and the OR. So how logic operations with NAND gates? How are we going to implement these other gates with the use of NAND gate? Yeah. Not AND. Where are the examples? It did not show. Wait. Okay, let's try to show how we can implement the NAND gate. How is this going to be equal to x to an inverter with x input? Did it say how many? For example, if we have a 2-input NAND gate, we have X. We can implement the inverter. If we use 1, connect the other input with 1. We have the function will be equal to X ANDed with 1, and then we complement because this is a NAND circuit. So X ANDed with 1 is 1, so X prime. Therefore, we have implemented an inverter with a 2-input NAND gate with 1 at the other input. See? For the second, we have the AND. How can we implement the AND? It's already shown here. We have X, Y. We use the AND and we just invert the result. We know that an inverter can be implemented with an AND gate. So we just implemented an AND excuse me. We just implemented an AND function and logic gate functionality with the use of NAND gates. This inverter is considered a NAND gate as we have shown here. For the OR functionality, how to convert the NAND gates into OR by using 2 inverters, 2 NAND inverters, and then another NAND gate. This is X prime, Y prime, then the complement of that is X or Y using the Morgan's theorem. Okay. That's why for the NAND gate, there are 2 possible symbols. This is the most common and it's called AND invert symbol for the NAND gate. And then the less common, the invert OR. Invert OR. Yeah. We know that by the Morgan's theorem, these 2 are equal. So an AND gate can be symbolized with an AND invert and then invert OR symbols. That's why the NAND gate is called a universal gate, because we can basically create the other logic circuits with the use of NAND gates. The implementation of Boolean functions with NAND gates requires that the function be in sum of products form. Sum of products form. And this is the equivalent circuit for that. For figure 3.8 in A, F is equal to AB plus CD. 3 ways to implement F equals AB plus CD. The very common is using 2 AND gates and then 1 OR gate, or with the use of NAND gates, that would be AB prime, which is an AND gate, AB prime, CD prime, then we add prime again. We know that this is just an AND gate. NAND gate. Another symbol for an AND gate, invert OR. These 2 are equivalent, yes. So we have just shown that we can implement this function, this common function, f is equal to ab plus cd or cd with the use of NAND gates. Another example, implement the following Boolean function with NAND gates. So how are we going to implement this Boolean function with NAND gates? First, we will try to simplify. The first step is to simplify the function into sum of products form. This is done by means of the map. We are using the Carnot map. We have 3 variables, so we are using the 3 variable K map. X, Y, Z. Min terms 1, 2, 3, 4, 5, 7. So 0 and 6. Min terms 0 and 6 are not included. How are we going to simplify this? We have 2 adjacent, and then 4 adjacent squares. Remember that we can't combine 3 adjacent squares. It has to be multiples of 2. Since we are trying to simplify using the variables, and 3 variables doesn't have anything in common. The last square doesn't have anything in common, so it has to be factors of 2. This one is x, and then what is this column? 0 is common, that is y, so xy prime. Well, here we have, this is column for y is common, which is 1, and then x is 0, this row, so x prime y. For this 4 squares, this is z, so that's at z, because everything is covered, all the rows are covered, and it's variable z. So the function is f is equal to xy prime plus x prime y plus z. How are we going to implement that with the use of NAND gates? Using NAND gates, we convert this OR. We use the invert OR. The OR invert, OR invert. Invert OR, yeah. Invert OR. Try to use the invert OR. Is there a pattern here? Let's try to check. A, B, C, D. A, B. It's just an AND of A, B, and C, D. Use the OR. Disconnect. Okay. Can you see the logic behind? If it's A, B, C, D, we use 2 NAND gates. You use 2 AND gates, and then you just add bubbles in between. Then convert the OR, the invert OR to an AND gate. So here, let's try to show to you. We have the function f is equal to xy prime plus x prime y plus z. So let's have AND gates here. X, y prime. Wait. This is x. This is y. We need to have an inverter here, because it's xy prime and then another AND gate. We have y prime. Let's connect it to an inverter. X prime y, then xy prime, and then z. Z will have to be connected to an inverter. Wait. Then let's add with this OR. We use OR. Invert OR. Connect it here. So this is our F, or we can draw it using, we just replace this inverter with an AND circuit. Just rewriting, but with the use of AND gates. We have Z. Is this right? Let's check the diagram. Yes. Y prime, it did not show the inverter. X prime, Y, right? Oops. Yeah. Z prime did not show here the inverter for Z. It's just Z prime. So it's the same. See the pattern? Can you see now the pattern in implementing this? Just replace, this is ANDed, and you can use AND. This is ANDed, you use NAND gate for that. And this is ORed, you use a NOR gate, because these two bubbles here, they will just cancel out, so it's the same function as this one. But note for Z, it's Z here, but we have an inverter here because we use NOR here, we negated here. So to cancel out, we must have two bubbles to cancel out this bubble here from the NOR gate, because this is Z, and not Z prime. So that's, and if you have this diagram, we replace the NOR gate with the NAND gate because they're the same. I mean, this is not a NOR gate, this is an invert OR gate. We replace the invert OR gate with the NAND gate. Implementing F is equal to A times quantity CD plus B plus BC prime, which is a Boolean function. So it says here that these are both equal. Let's try to check. Yeah. The first one uses AND OR gates, the second one using NAND gates. We know that this invert OR is just a NAND gate. Well, this is the typical NAND gate symbol. So amazing, using NAND gates we can implement any function. That's why it's called a universal gate. We know that these bubbles will just cancel out, so this is basically equal to this one. Okay. Convert all AND gates to NAND gates with AND invert graphic symbols. AND invert, yeah. This is the AND invert symbol. Convert all OR gates to NAND gates with invert OR graphic symbols. Check all the bubbles in the diagram. For every bubble that is not compensated by another small circle along the same line, insert an inverter, a one-input NAND gate, or complement the input literal. That's what we did here. We added an inverter because nothing compensates for this bubble here. So to have this bubble compensated, we added an inverter. Another example. Replace the AND gates with NAND gates. Replace the OR gates with invert OR. They are the same because there are two bubbles that will just cancel out. And here, replace the OR gate with invert OR. What happened here? And we replace the we should have an inverter here, but instead of adding an inverter, it complemented the input. So instead of C, it becomes C prime. So same as adding an inverter. And then instead of D prime, it changed it into D, so that the bubble here will be complemented. Then for the AND gate, it replaced it with an AND gate, then added an inverter here to compensate for the bubble. NOR implementation. Let's go to the NOR implementation. NOR operation, dual of the NAND operation. Yeah, it's just a dual of the NAND operation. We have already explained what dual property is. Logic operations with NOR gates. So the NOR gate is also a universal gate because we can still implement other logic gates with the use of NOR gates. For the NOR gate, instead of invert OR, we have the OR invert, which is the common symbol for the NOR gate. And then the less common symbol is the invert AND. Invert AND. This is x prime y prime z prime, which is by the Morgan's theorem is equal to x or y or z complement. Two graphic symbols for the NOR gate. The OR invert, which is the common, and the invert AND, which is the less common. So have an example. This is the function f is equal to a plus b times the quantity c plus d times e. And this is equal to this Boolean function. We OR a b, we use the OR gates with a bubble, so that's the NOR, and then the AND gate with a bubble at the inputs, which is the another NOR gate, but with the use of an invert AND symbol. Same concept. We know that these two bubbles here will cancel out. These bubbles here will cancel out, and it becomes this E prime. e prime with the bubble that will cancel out. So basically this is equal to this function. We just replaced the OR gates, this OR here with the NOR, and then the AND gate with invert AND symbol, because the bubbles will just cancel out. So we just implemented this function using NOR gates. Instead of OR and AND logic gates, or instead of using NAND gates, we used NOR gates. There are other two-level implementations, other types of gates aside from NAND and NOR gates. We have wired logic. We have this term wired logic. This is when NAND or NOR gates allow the possibility of a wired connection between the outputs of two gates to provide a specific logic function. Then wired AND gate. Wired AND gate is not a physical gate, but only a symbol to designate the function obtained from the indicated wired connection. A wired logic gate does not produce a physical second-level gate, since it is just a wire connection. I don't quite haven't experienced this wired logic, but it happens in synthesis that when the synthesis tool produces wired logic, there are times when the synthesis tool automatically the computer software results in a wired logic. I'm not sure if this is a warning that needs to be resolved during synthesis. I have to review on that. Anyway, let's move on. This is the symbol for the wired logic. Wired AND logic with two NAND gates for letter A, and then we have the letter P, wired or in intercoupled logic gates. So the symbols. Let's move on. Degenerate forms. These are gate combinations that degenerate to a single operation. For example, AND followed by an AND gate in second level, same as a single AND gate. It's called degenerate form. Non-degenerate form produce an implementation in sum of products form or product of sums form. For example, AND or NAND or NAND, etc. Okay. AND or invert circuits and NOR circuits. Examples are this. Just read this one. Don't think I need to explain this. Exclusive OR functions. Please see the book for more examples. Let's discuss this a little. Exclusive OR function. We recall that exclusive OR has the symbol this, and it means that x prime y or x, y prime. Only one is high. Either x is high or y is high. So x exclusive or 0 is x. Let's try to check. X prime, let's see, y is 0. Plus x 0 prime. So that is x prime times 0, that's 0. Or x 1, so that's x. Therefore, the exclusive OR of x exclusive OR with 0 is x. X exclusive OR with 1 is x prime. Let's check. X exclusive OR with 1. So x prime 1 plus x 1 prime, that's x prime. So x prime. Try to remember this. This is useful in simplifying functions. Exclusive OR, x exclusive OR with 0 is x exclusive OR with 1 is x prime. Then x exclusive OR with x is 0. Yeah, it will always be 0 because we know that x exclusive OR with y, we want that only one is high, the other is low. If if x is high, y must be low, and then if x is low, y must be high. So if we perform this operation, x exclusive OR with x, then both are the same. We know that they can't be the same. Therefore, the result is 0. Let's try to prove it. X prime, y is x. So x plus x times y prime, which is x. That will always be 0. X exclusive OR with y prime. X exclusive OR with x prime, that will be always equal to 1. Can also perform this to prove it. Then x exclusive OR with y prime. Let's try. Substitute it to y. So x prime, then our y is y prime, plus x y prime, our y prime is y prime, so y. So x prime y prime plus xy, which is just a complement. The complement of the exclusive OR y. We know that this is the complement of the exclusive OR. Exclusive OR is commutative and associative. So A exclusive OR of B is just equal to B exclusive OR of A. Same as here, associative, the groupings. If we regrouped it, it's the same answer. For example, x prime plus y prime times x plus x prime be equal to, yeah, this is not a clear example. Anyway, exclusive OR implementation. From the equation itself, we will be using OR and then AND gates and then inverters. That's the common. Exclusive OR with AND or NOT gates. Exclusive OR with NAND gates, we know that we can replace this with NAND gates. We replace the AND gates with NAND gates, and then the OR gate with invert, or just another NAND gate. And then what happened here? Just did a little manipulation here. Anyway, this is from the equation, this example. Okay, it expanded. What happened? Expanded the equation to form this NAND gates. So this one is equivalent to this one. Anyway, let's explore this one later on. Just move on to the more important. We have here an example of a 3-input add function and then a 3-input even function. Add function, add number of variables, be equal to 1 to get 1 output. We have already discussed an example of an add function, the add parity, while trying to evaluate the add parity bit. Add number of variables be equal to 1 to get 1 output. As an example, exclusive OR of A, B, and C. We know that an exclusive OR function is an add function. Here, it uses exclusive OR and then exclusive NOR. This is an example of a 3-input even function. Parity generator. This is a circuit that generates the parity bit in transmitter. Recall that a parity bit is used for the purpose of detecting errors during the transmission of binary information. In the transmitter, we have the parity generator, which generates the parity bit. This is useful in detecting errors. In the receiver, we have the parity checker. This is a circuit that checks the parity in the receiver. For an even parity generator, this is the truth table. If we have 3-bit message, we add the parity bit. Since it is an even parity generator, we add the parity bit to have an even number of ones. So here, 0, parity bit is 0 because number of ones is 0, which is we consider even. Here, 1, we have an odd number of ones, so we add 1 in the parity bit to make the number of ones even, which is 2. 1, and then we add 1 to make 2 ones. Then we have already 2 ones here, which is already even, so we add 0 in the parity bit. For the last one, we have 1, 1, 1. That's 3 numbers of 1, which is odd. We add 1 in the parity bit to make the number of ones even. Now the total number of ones is 4, which is now even. The implementation of the circuit, 3-bit even parity generator. As simple as that. We used exclusive ORs. P is equal to 1 if odd. If the P is equal to 1 if the total number of ones in XYZ beats XYZ is odd. We know that exclusive OR, using exclusive OR gates, makes the function an odd function. This is observed in the truth table. This is an even parity, 3-bit even parity generator, because P is 1 if the total number of ones in XYZ is odd. So don't be confused. For a 4-bit even parity checker, we still used exclusive ORs. We know that exclusive OR function is associative, so it doesn't matter the order. They can be interchanged. We use 3 exclusive OR gates here for XYZ, including the parity bit. This is for the checker, parity checker. In the receiver, does it have explanation here? The parity bit P is added to the 2 input XYZ to produce an even parity. Yes, we have already explained that. If input XYZ total number of ones is odd, P equals 1, giving XYP total number of ones even. That's why circuit A in figure is an even parity generator. C in the figure is a 4-bit even parity checker. If total number of ones in XYZ P is odd, C is 1, which indicates an error, since what is expected is an even number of ones. So C, if C is 1 here, then we have an error, because C becomes 1. This is an odd function, right? 3 exclusive OR gates. We use 3 exclusive OR gates, which is an odd function, and that will result into a high C is equal to 1 if there is an odd number of ones. And C is equal to 1 indicates an error. C is equal to 0 means that the circuit is functioning. We receive the correct bits, because that would mean that there's an even parity, because this is an odd circuit. So that ends our discussion for section 1.3. I'm just kind of having a hard time explaining this part. Let's move on to the next topic, which is the most exciting part, HDL with Verilog. We are going to start using Verilog. That will be on my next video. Thank you for watching, please subscribe. See you on our next video, which is 1.4 HDL with Verilog.